and we were looking at the conservation of energy, specifically mechanical energy. And we talk about different kind of energy. So we talk about kinetic energy, that is the energy when something is moving. We talk about gravitational potential energy, that is when something is at a different height or someone changes its vertical position. And we talk about spring potential energy, that is when something is being compressed by a spring. And I think those are the three kind of energy that we were talking about. And what we the last part that we were looking at was a car in a roller coaster that was kind of doing a loop, and you're gonna help me. You need to help me with this. So we did something like this, and then it did something like that, right? So can you tell me the initial values? What is the initial height? 20 meters. So I'm gonna call this 1, 2, and 3. So the height at 1 was 20 meters. The velocity, 5 meters per second, and the mass, 150 kilograms. Perfect. And now the height of 2, how much? 5 meters? 10? 10 meters. We don't have the velocity. We found the velocity, right?
Yeah.
Well, which one? What was it?
14.86.
14.86 meters per second. And what was the last height?
30.
30. Okay. And that was the last part, right? Okay. So here in this system that we are considering, we are assuming that there's no friction anywhere. Okay. So the mechanical energy that we're gonna have everywhere has to be conserved. So whatever energy you have at point 1 has to be the same energy at point 2, have to be the same energy at point 3. Actually, it doesn't matter where you pick, the energy has to be the same. The only difference is going to be how much of one kind of energy you're going to have with respect of the other ones. At some points, for example, at the bottom of the loop, you're not going to have any potential energy, any gravitational energy. Everything's going to be kinetic energy. And maybe there's going to be one point at which you're going to have all of it is going to be potential energy, but nothing's going to be kinetic energy, and so on. So the percentage, the ratios between the two is going to change. But the net effect is that the total energy has to be conserved. At the moment that you introduce friction, all this goes to hell. But right now, we assume that the energy is going to be conserved. Okay? So we're going to find the energy at point 3. And you can do it two ways. You can find the energy, and you can say, well, the energy at point 1 has to be equal to the energy at point 2. At point 3. Or you can say that the energy at point 3, the energy at point 2 is equal to the energy at point 3. So you can do it either way. You can go from 1 to 3, you can go from 2 to 3. Okay? So I'm gonna let you guys do this to find what is the velocity at point 3. I'm gonna let you guys do it on your own, and then we'll do it together. So I'll give you 10 minutes, and then we go back. Cooper, are you supposed to be here today? Or are you on Monday?
No, I'm supposed to be there Friday. I just never come to class.
Never?
I think I came the first time.
Can you come at least? There you are.
Hi.
Okay. Now I can see you. Yeah, I have no idea who you are. I see your exams and I see your homeworks and everything looks go okay. I will never recognize you.
Yeah, I just do it in my dorm just because it's working fine. So.
Okay. Well, if it's working, it's working. Okay. Thank you.
Yep.
I'm pretty sure there are other people that have never been here. I just noticed him. Brian comes here Fridays. Grace sometimes twice. There's a lot of people missing today.
Hold on.
You're not there? You're not? What?
No, I don't have to.
She's into the much
I agree.
we sometimes have games before and after.
Yes, let me go through my name.
But I think it had little to do with
Oh, no, I don't have to. Okay, hold on. Hopefully. it has
By the way, I like that it's almost do this. That's pretty cool. Are you sure?
Yeah, that's where I'm at too. I did the math, so I did the back to the math.
Okay, people are getting weird results over here. So people in the chat, if you can write down what you're getting for your velocity, I'll try to do it. I was hoping not. Thank you, Kennedy. Thank you, Mary. What was I saying?
No, I did it, negative two.
A negative? Everybody's getting a negative?
Yeah, I got knocked out originally. Well, I can't finish it because I can't do this.
What do you mean you cannot finish it?
It says error. Do you want me to write that down? Yes.
Is error on your calculator?
Yeah, because you can't use vertical and I remember. Maybe you can. Not in the settings are in there. What negative comes what negative is. I did this yesterday. It is so weird. But I tried it yesterday. And I tried it. Good idea. Please. I don't know what is going on with you. How are you getting a license? Kids. Right? Am I doing it wrong?
Do you guys get something like that?
Yes. Yeah.
Yeah, on the chat, did you guys got something like that?
I'm back here.
Okay, so we can get a result. Like from the math point of view, this problem can be solved. You have a square root of a negative number. Well, that means that it's an imaginary number. Okay, so math can help you solve this problem. But from the point of view of physics, what the hell does an imaginary velocity even mean? So it doesn't have any meaning. It doesn't exist. So what does this problem trying to tell us? What is that the results trying to tell us? Well, basically what's happening is that the energy that you have at the beginning of the problem, this energy that you have here, is not enough to bring you all the way up. There's gonna be one point when you are climbing that last hill that you're gonna be running out of kinetic energy. So you're gonna come to a full stop, and then you're gonna stop there and you're gonna start going back. So when you reach these kind of problems, when you don't have enough energy to reach stage 3 or stage 4, whatever, you're gonna get real results like negative velocities, or you're gonna have an extension on a spring that's gonna be larger than the extension of the spring itself. And that basically means that the solution, the problem doesn't have any physical meaning. You don't have enough energy to reach the top of the hill. Okay? So just be careful. The math can tell you that yes, it can be solved, but in reality it doesn't have any physical meaning. And Tarim, double check your math. Hayden, that makes sense?
Yeah.
Are you sure?
Yeah, I got the answer, but I didn't use those numbers. So I don't know what I did.
What you got at the end?
I got negative 171.
Oh, then you're okay. What happens in between, it doesn't matter. Just got the last part. Okay, makes sense? Okay, now we're gonna do a different kind of problem. We're gonna be doing another ballistic problem. But now this is a ballistic pendulum. This is called ballistic pendulums. And it's pretty much the same idea that we talked about last time when we have that block being displaced after being hit by a bullet. The difference now is that we have the block hanging from a string, and we're gonna have a bullet being fired to that block. Okay. Now, after the bullet hits the block is gonna start swinging. So it's gonna go from its vertical position, it's gonna be swinging. And it's gonna reach a maximum deflection. So it's gonna have a maximum deflection, and then it's gonna come to a stop, and then it's gonna go back. So I'm gonna have the angle, and you can imagine that here, I'm gonna have a velocity of 0 meters per second. Okay, so what I want to find out is what is that maximum angle of deflection? What is that theta max? Now, this is a long project. This is a long problem. So just if you get lost or you want me to go back, just let me know and I'll repeat. Now, this problem or this kind of problems have to be divided in 2 parts. One part is going to be the block having that collision with the block, the bullet having the collision with the block, And we're gonna be doing that using conservation of momentum. And I'm gonna call this part one. So part one is gonna be conservation of momentum. Okay, part two is actual swinging of the block with the bullet. And that swing, we're gonna, this is gonna be part two. And part two is gonna be with conservation of energy. Okay, and I can explain why we need to do it this way, okay? So right now I'm just gonna solve the problem, we're gonna get the result, and then we're gonna look at why we need to do it with conservation of momentum and conservation of energy, okay? So I'm gonna do part one first. I'm gonna do the conservation of momentum, and then I'm gonna do part two. So for part one, I'm gonna assume that I have the mass of the bullet to be 20 grams. And I'm gonna have that the initial velocity is gonna be 600 meters per second. And I'm gonna assume that the mass of the block to be 10 kilograms. And the initial velocity of the block is gonna be 0. So you're just hanging there. And the other thing that I need is the length of the wire. And I'm gonna say that the length of the wire is 2 meters. Okay. So what I'm gonna do first is I'm gonna try to find out the velocity of the block and the bullet after the collision of the bullet. Okay. So to do that, we have done this problem before. So I'm gonna have the mass of the bullet, the initial velocity of the bullet plus m2, the initial velocity of the block. And because the bullet gets stuck in the piece of wood, then the two masses are going to be having the same velocity. And I'm going to call this velocity at point 2. I know that the velocity of the bullet, the velocity of the block is 0, so it doesn't have any momentum. So here I'm going to have 0.02 times 600 is going to be equals to 10.02 times v2. And the velocity at point 2 is going to be 0.02 times 600 over 10.2. And
what? Okay.
I'm rounding up, you end up with 1.197, so I'm rounding up to 1.2. So this is the velocity of the block and the bullet. So when the block this is going to start moving at a velocity of 1.2 meters per second. Okay. So now I'm going to do part 2, and part 2 is going to be using conservation of energy. So this problem is basically having an object with a mass of 10.02 kilograms and a velocity of 1.2, and this thing is going to start swinging, and it's going to reach a maximum deflection. Okay, so what we have here is going to be a conservation of energy. There's going to be a change in kinetic energy to gravitational potential energy. As the mass starts swinging, the height of the mass is going to start increasing, and then it's going to reach a maximum height, and then it's going to start coming down. So there's going to be a change in height here. Okay, so I'm going to try to find out what is that change in height. Okay, I'm going to set my frame of reference here at the bottom of the pendulum when it starts swinging. So, and I'm going to call this point 3. Okay, so I'm going to basically say, okay, the energy at point 2 has to be equal to the energy at point 3. And at point 2, what I have is basically kinetic and potential energy and the 2 points. So I'm going to have 1/2 of the mass B2 squared plus mgh2 going to be equals to n B3 squared plus mgh3. Okay, the gravitational potential energy at point 2 is going to be 0 because that's where I'm setting up my frame of reference. So this guy is going to be 0. And the kinetic energy at point 3 is also going to be 0 because if this is the maximum height, then the block is going to come to a full stop and then it's going to start moving down. So at that instant, you're going to have the kinetic energy equals to 0. Yeah? So I can find that height. The masses are going to cancel. And then I'm going to have that the height is going to be equals to the square of the velocity over 2 times gravity. So this will be 1.2 square over 2 over 9.8. And I get 1.03 meters, which is 7.3 centimeters. Yep. So this thing is going to swing. The height of the block is going to raise by 7 centimeters, and then it's going to come to a full stop, and then it's going to start moving down again. Okay. So I got this delta H, but that doesn't help me solve the actual question from the problem. That's to find out what is this angle. So that last part is just geometry. So I'm going to do it over here. I told you, it is a long problem. Okay, so I'm going to exaggerate the dimensions and everything just to make it clear. So I have the initial position of the block, the final position of the block is going to be somewhat like that. And this height is delta H. Okay, the length of the wire doesn't change just because you are oscillating. So this length of the wire is going to be L, and this length of the wire is also going to be L. Yeah, and this guy over here is going to be L minus delta H. Okay, so notice that here I have this small triangle over here that I'm going to redraw outside. Okay, so this side is L, this is L minus delta H, and this is angle theta. So cosine of theta is going to be adjacent over hypotenuse. And then from here, L cosine of theta is going to be L minus delta H. And then delta H will be L minus L cosine of theta. Oh crap, no, never mind. You don't need this. So theta will be the cosine inverse of L minus delta H. Okay, so from here I can substitute values. So I know that L is going to be 2 meters. Delta H is 0.73 meters. Here I'm going to have, again, 2. Okay, so that angle of deflection is going to be 15 degrees, 15.5 degrees. Okay, makes sense? People there in the chat? Yep. Erin, everything clear? Ish? Okay, so the question is, why cannot use conservation of energy everywhere? What if I have this block? What if I have the block with a bullet? Why cannot use conservation of energy between these two steps? Why do I have to use conservation of momentum? If I know that the energy has to be conserved, then it will make sense that the energy that I have before the collision has to be equal to the energy after the collision. But we don't do that. We need to use conservation of energy. And let me show you really quick. So I can calculate, I have the mass of the bullet, which is 20 grams, and I have the velocity of the bullet, which is 600 meters per second. So I can calculate the kinetic energy of the bullet. I also have the mass of the block, which is 10 kilograms, and I know what is the velocity of the block, which is 0. So I can also calculate what is the kinetic energy of the block. And in this case, because 0 velocity is going to have 0 kinetic energy. And I know what is the mass of this thing. So I know that this is 0.02. And I know what is the velocity of these things. We calculate that velocity using conservation of momentum. So this is going to be 1.2 meters per second. So let's do this thing. So these first two rows, Kennedy and Mary, so those two rows, calculate what is the kinetic energy of the bullet with the block and the bullet. Okay, so calculate what is the kinetic energy after the collision. The first two rows, calculate what is the kinetic energy before the collision. Yes, you mentioned. So you calculate the kinetic energy of the bullet and the block. What is the kinetic energy here? And so in the chat, if your first name is before an F, then do the conservation of energy of the bullet and the block before the collision. And if your first name is after the letter F, then you do the bullet and the block after the collision. And when you're done, just put your results. You got it, Mary?
I think I did the wrong one. Which one was supposed to be in? After.
Yeah, you did after. I'm laughing because actually I also forgot which one I told you to do.
I got it. Make me feel like it's harder than what I did.
No, you don't know why. That's part of the problem. People think it's harder than it actually is. No, you use a planar formula. It just flows. Yep. You forgot it again. Why did you
I
miss
have
that?
that, but I have a buffer. You have what? The ponchos.
Oh, you do both. See, if you do it, you go ahead and like, there's no surprise, and then like jokes don't make sense. Use I don't know. Okay, so you guys should have found that before the collision, if you calculate the kinetic energy of the bullet and then you add the kinetic energy of the block, you end up with an energy of 3,600 joules. And if you calculate the kinetic energy of the block and the bullet after the collision, you end up with a kinetic energy of 7.2 joules. So they are not the same. So the energy is not conserved. The energy at point 1 is not the same as energy at point 2. And that makes no sense because if we have talked about something, is that there has to be conservation of energy. But we don't have that here. So the question is why? So these kind of collisions, when an object gets stuck in another one, these are called inelastic collisions. Okay, it's the same case when you have two football players tackling each other, or when you have a piece of clay that you throw into something, or two pieces of clay thrown into each other and they get stuck together. When you have that the two objects or the different amount of objects that they are colliding, they end up with the same final velocity. They get stuck together. You have an inelastic collision. So when there are inelastic collisions, you can imagine that there's a deformation of the object. So in this case, the block, when the bullet goes inside it, the bullet gets deformed, the wood gets deformed too, and in that deformation, there's a loss of energy. There's an energy that can transfer into heat. There's an energy in the that is lost in the deformation. And the equation that we have seen don't count for that deformation. All the physics that we have seen, or many of the physics that we have seen, assume that our objects don't deform or don't count for the deformation. So we don't see where that energy is lost. You can think of it as being lost in the sound, it's being lost in the heat, it's being lost in the deformation of the object. So when you are working with inelastic collisions, there's no conservation of mechanical energy. Or there's no conservation of kinetic energy, no conservation. Okay, so you have to be careful. There is a different kind of collisions that's called elastic collisions. That's the example of having billiard balls colliding with each other. There is no deformation of the object, they just bounce from each other. So when you have elastic collisions, then you have conservation of momentum and conservation of energy. And we're gonna be talking about those next week. But right now, just one of the things that you need to figure out when you have these kind of problems is, okay, what kind of collision do I have? Do I have conservation of momentum? So do I have an elastic or inelastic collision? And if you have an inelastic collision, you need to work with conservation of momentum. Okay? Make sense? Okay. So we're gonna do one more problem, and then I'll let you guys go. It's 20 minutes. I cannot let you go now. I don't know. I mean, I would love to, but it looks bad, and my boss is around there, so he will notice. We can yeah, I'm not gonna stay here for 20 minutes. Okay, I forgot the program. Huh? It's a sign. Oh, I have it here. Oh. You see, that's one of the advantages of having the same notebook.
Now everything's gonna be mixed up.
But what?
I said, but now everything's gonna be mixed up.
It's already mixed up. Huh? What the hell is this? It's not fair?
No, it's not there.
Why is it not fair?
Not there. In the notebook. It's gone.
Oh, there it is.
Jesus.
I have to say, I screw up a lot in the morning. You guys get the refined version. There's most of them are sleeping, so that's okay. So it's gonna be a ballistic pendulum, same idea, but now you're gonna try to find out what is the velocity of the bullet. Yay! I'm glad that I can see, I'm not seeing half of your face expressions. I just imagine. I imagine that you're smiling. I choose to imagine that. Okay, so I'm gonna have a bullet. The bullet has a mass of 50 grams. They have an initial velocity that I have no idea where it is. And again, it's hitting a block. The block has a mass of 1 kilogram, and it has an initial velocity of 0 meters per second. The length of the wire is 1 meter. The bullet hits the block, it gets stuck in the block, and the block starts oscillating. And what I know is that the maximum oscillation makes 20 degrees with a vertical. Okay? And what I want to know is what is the initial velocity of the bullet. Okay, give it a try. This is exam problem. This is classic problem in the exams. Emma, how are you doing? Good, good. You've been very, very quiet. I'm gonna see who's skipping class today.
Skinner. She's skipping class.
So in this problem, it's better to start from the end. Yeah. That's all conservation element. But you
Sorry, like, because I was confused, because I got 0.
yeah. So for this problem, you're gonna start with part 2 and then with part 1. So this is part 2, and this is gonna be part 1. Part 1. So start with part 2. So from geometry, you can find delta H. And once you find delta H, you can use conservation of energy to find the velocity at the bottom of the velocity at the bottom of the pendulum. Once you have that velocity, then you can go to part 1, and you can use conservation of momentum to find the initial velocity of 1. So because 600, this one will be 0, because you can assume that at the bottom of the swing, you lose all your is 0, and then you can find this. Why is that 0? So this delta H that you are calculating for, that's a difference between the two positions. So there's going to be a difference between the bottom and the top. So this is 1, this is going to be 1. And basically, yeah. So it becomes this. Yeah, so this is going to be kind of your reference. So you can assume that it's 0 and then the delta H. And double check.
but yeah, double check that. So this one, yeah. This side here.
No.
L. So this one over here, what you find is L minus. Oh, you did all of it? Whoa. Check your math. Yep.
I got some good stuff. Hey, that's what
Yes, this will be 1 minus t.
over. I'm gonna go with it.
Okay.
I don't think that's.
You may hear about the day.
Okay.
You know, yes, you did, oh, come on.
My answer doesn't make sense.
You have,
Okay, we're not gonna have time to finish all of it. I'm just gonna find delta H and find the velocity of the block after the collision. So you're gonna have something like this. This is gonna be 20 degrees. 20 degrees. And you can imagine that the block is doing, just swinging along about that. We're gonna have, this is gonna be the hypotenuse, and this is gonna have a length of 1 meter. This here is also gonna be 1 meter, and this is gonna be delta H. This is what I want to find out. So this side, this adjacent side of my triangle is going to be L minus delta H. Okay. So I'm going to have that cosine of 20 is going to be L minus delta H over L. So L cosine of 20 is going to be L minus delta H. Delta H is going to be equals to L minus, wait, L cosine of 20. Did I get it right? Yeah. Okay. Substituting values. This is going to be 1 meter minus 1 times cosine of 20. So, Alisa, I think this is where you got it wrong. So this will be 1 minus cosine of 20, I think it's 0.93 or something like that. Yeah, it's 939, blah, blah, blah. So you end up with delta H to be 0.06 meters. So the change in height of delta H is only 6 centimeters. Okay, I think most of you got it, or you got the 0.93. So you just need to look at the geometry to find delta H. Okay. Now, with this, I can find what is the kinetic energy of the block after the collision. So I'm gonna have 1/2 of the mass, the velocity at 2 square, plus mgh2 equals, oh, it's not gonna be, 1/2 velocity 3 square plus mgh3. Okay. The kinetic energy at this point is gonna be 0, because we're assuming that that's the maximum height. So when something reaches the maximum height, you're gonna have velocity of 0. And the gravitational potential at point 2 is gonna be 0, because that's gonna be my reference point. So then I'm gonna have 1/2 of m dr squared equals mgh3. And this h3 is what we found here. Okay. The masses are going to cancel. I'm solving for the velocity. So the velocity at 2 squared is going to be 2gh3. So the velocity at 2 is the square root of 2 times g times h3. So this will be 2 times 9.8 times 0.06. I get a velocity of 1.08 meters per second. Okay? Make sense? Yeah? Okay. We're going to stop here, and then we're going to continue on Friday. Okay? And Friday, we're going to do the second part. Eleanor, you checked your math?
I did, I still am not sure.
Yeah. Did you get the same result?
Yeah, I made this.
Mary, did you get the same result?
I got the right answer for the velocity. It's in the second part that I think I screwed up. I don't know what it is.
But you got the 22 meters per second?
Yeah, because like I got the delta H equals 0.06. I got the velocity equals 1.08. But I could have been plugging things in wrong.
No, I think you are correct. Yeah, no, you're fine. It's 22 minutes. Kennedy, I opened your exam, so you should be ready to do it. And I don't know if you have done the exam already.
Yeah, I did it yesterday.
Oh, okay.
Yeah, I submitted it.
Okay, I'll double check. Okay. Have a good day. See you. Thank you, Sylvia. See you, Mary. Have a good day too, Elizabeth.